Here's an example of an improper integral, and I actually chose this one specifically because there's something about it that could catch you off guard if you weren't paying attention. So I want to expose you to that so that you'll catch this on a homework or a test problem. All right, so what I noticed about this guy, the reason I said improper integral is 1 over x cubed has a vertical asymptote at 0. And it's not just the fact that it has a vertical asymptote, it's that the vertical asymptote happens between -2 to 1. If I had been going from 1 to 10, it would have been no problem. I would have integrated like normal. Because the asymptote happens between -2 and 1, then I have an improper integral. Fortunately, I know how to handle these guys. What we'll do is we'll actually break this apart into 2 integrals, right? We'll go from -2 up to the asymptote, 1 over x cubed dx, and then we'll integrate from the asymptote on the rest of the way up to the last endpoint at b, 1 over x cubed. Okay, so graphically it would look something like this. Right, you'd have 1 over x cubed to the right of 0, and then 1 over x cubed to the left of 0. And then you see the vertical asymptote at 0, of course. And then we're integrating from -2 up to 1. Okay, so we have this area going on here. So we go -2 to 0 to get this region, and then from 0 to 1 to get this region. Now, if it's an improper integral because of a vertical asymptote, we know how to handle this. What we'll do is at the vertical asymptote, we will put a kind of a dummy constant, a dummy letter. And so let's do that. I'll just focus on the first one right now. We'll get to the second one when the time comes. So we'd go integral from -2 up to, we'll just call it b. I mean, you can use a, b, c, k. The letter doesn't matter, but we'll just need a number here of 1 over x cubed dx. And then, like I said, we'll do this one when the time comes. And then we'll take the limit of that as b pushes its way on up to 0 from the left when we're finished, right? So the idea, if you can see this small on my graph here, is we'll go from -2 not up to 0, but just short of 0, and we'll get this area, and then we'll push our way to the left, to the right, on up to the vertical asymptote to fill out the rest of the way, right? But we stop short so that we can use the fundamental theorem of calculus. Okay, and for this guy here, I'm not going to write it, but we would go from a up to 1 and take a limit as a goes to 0. Let me just work on this guy here, and then I'll come back and do this one as needed. All right, so let me come to the next page here. We integrate 1 over x cubed, we would get, let's see, that would be x to the -3. So we'd get -1/2 x to the -2, bracket from, let's see, lower limit was -2, upper limit was b, and then we'll take the limit, of course, as b goes to 0 from the left. Let's plug in a b, limit as b goes to 0 from the left. We'd get -1 over, here's a 2. This would be b to the -2. So let's put in the denominator, make it b to the +2 like it should be. All right, and then minus, but that's negative, so this will make this a plus. 1 over, right, 1 over -2 to the -2. In other words, -2 to the +2, which would be 4 in the denominator, though, because of the negative exponent there. Okay, now if you let b go to 0, this term especially is going to blow up to infinity. And then if you add a fourth, that's not going to affect much of anything. So this part right here would be infinity, right? So this limit right here is going to diverge. And that's before talking anything about the other integral and the other that we're going to add to this in a minute. And one thing we know about limits going to infinity if this guy's going to diverge and blow up to infinity, there's not really anything this guy can do to stop it. Like if this was doing something else or going to 10 or what have you, that's not going to change the fact that this whole integral right here is going to diverge. Now, so we're done with the problem. This integral diverges. That's really all we need to say. It's not going to converge to a finite amount. But the reason I picked this example is this is very easy to overlook. You could work this incorrectly. Here, I'll do this in green. And just to be clear, this is the wrong way to do it. This is the wrong way to do it, but I've seen plenty of students do it this way. They see a closed interval, -2 to 1. They say, oh, great, it's not improper. It doesn't go to infinity or anything like that. You can integrate 1 over x cubed. You would get -1/2 x to the -2. Bracket from -2 to 1. You'll pop in a 1. You'll pop in a -2 and subtract, right? So you'll get a number here and you'll get a number here and you'll subtract them. But you're trying to use the fundamental theorem of calculus, but the fundamental theorem of calculus, unfortunately, is not valid for this discussion. Well, why not? Well, you remember the criteria to be able to use the fundamental theorem of calculus was that you had to be integrating over a closed finite interval, and your function had to be continuous, and clearly this is not continuous on this domain. So I caution you, when you're doing these problems on your test, make sure that there's no place on your interval where you've got an asymptote or anything like that. Now, again, I'll reiterate, it's not just the asymptote. The asymptote has to be on the interval that you're integrating, because again, if we were integrating from 1 to 10, we could have done it this way and it would have been perfectly normal. But anyway, breaking this apart and doing it as we should, the limit diverged, which means that this improper integral diverged.